Still a little sleepy, I guess. I don't know. So here on November 11th, Remembrance Day. So yeah, everything, you should know everything already for assignment 3. So today we're starting new material that will be on assignment 4. We're doing infinite sample spaces. We'll see. I don't know. It may take the whole class, or it may be a little bit shorter than the traditional lectures. If it's a bit shorter, then I've picked out some exercises from the textbook, and we can review a few concepts like what is independence. So what's the difference between a disjoint events and independent events, and how those would affect how you determine the probability of certain outcomes. But we'll see how it goes. Any questions before we get started? Okay. I'm going to get set up here. All right. So infinite sample spaces. So up till now, we've talked about all of our sample spaces have been finite, but it is possible that you can have an infinite set. So, and let's see how that affects the probability of things. And I don't know if there's any people who have taken English classes or fans of Shakespeare, but Shakespeare wrote, was it Shakespeare who wrote it? My goodness. No. Anyway, Rosencrantz and Guildenstern Are Dead is a famous play that was made into a movie. And in the beginning of it, Guildenstern is flipping a coin. They're talking, of course. It's supposed to be a comedy. And he's flipping a coin. It keeps coming up heads, 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 heads. For as much as he keeps trying, it comes up heads. And there's, one line here: a weaker man might be moved to re-examine his faith, if nothing else, at least in the law of probability. So the thing about the law of probability, as improbable as all of this is, it's still possible. It's just yeah. And then and no matter what he does, he flips heads, 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 and then eventually at the end of the scene, he flips tails, and it's sort of an ominous note. But anyway, that's so the idea that you can flip a coin a number of times until you reach tails, or as we're going to talk about heads, means that hypothetically he could flip this up to, not infinite, because infinite's not a real number, but he could keep going conceivably forever, right? So we have to account for that. Okay, so already I think something wrong with my animations. Anyway, there's something wrong with PowerPoint in general. I seriously just did this, and now it's, anyway. So up until now, all of the sample spaces have been finite sets. So as we just talked about, we can have sample spaces that are infinite sets. So if I do something, if I take a fair coin and I flip it until it comes up heads for the first time, well, I don't know how many flips that's going to take. So one thing I do know is that all coin flips are independent. So then my sample space will look something like this. I will have, I could flip a heads in the first, yeah, it's characters from Hamlet who got killed off screen. And then for a second there, I thought it was, I thought Shakespeare wrote it, but I don't think that's true. Shakespeare wrote other comedies, sort of silly plays, but I don't think he wrote that one. Somebody else, maybe, I don't know. Anyway, so in our sample space, we can get heads on the first try, or maybe we flip tails once and then flip heads, or we flip tails twice and then flip heads. And essentially this can go on forever. So if we used sort of a set builder notation, then we could express it as I flip tails a number of times that's greater than or equal to 0, and then finally I flip heads. And so all possible values that I could get from that. So now we want to, we want to figure out, we can figure out the probability of any sort of individual event. So if I have n tails and 1 heads at the end, then I can, since these are independent events, well, first of all, I take the conjunction of all these events. So flip 1 is tails, flip 2 is tails, up to flip n is tails, and then flip n plus 1 is heads. And since these are all independent, then I can determine the probability of them by taking the product of all the individual probabilities, right? So then I take the probability that the first flip was tails times the probability that the second flip was tails, and so on and so forth, finally times the probability that the nth plus 1 flip is heads. All right, so if I know n, I can determine the probability of this outcome from our infinite sample space, right? It is simply 1/2 time to the power n plus 1, right? Because I have n plus 1 terms here, and each one occurs with probability 1/2. Okay. So we know that our sample space of probabilities must sum to 1, right? That's sort of this rule that we haven't revisited in a while, but basically my sample space, each outcome in my sample space is mapped to some probability between 0 and 1. That's what this means. And then when I sum all the events in my sample space, they must sum up to 1. So I have an infinite number of them, but they still must sum to 1. So yeah, so we will look at how we can actually make sure that our sample space here does sum to 1. So that's going to take us into, we're going to review. Some of this may have been stuff you've seen before in 1805, but we will review how we the ways that we can express an infinite series and how we can sum up an infinite series. So let's say I have an infinite sequence, A0, A1, A2. Each of these is a real number, and we want to define the sum of these numbers. So if we have finite many, say there's capital N numbers in this sequence, then we can define the sum by this, right? So we use the sigma notation, n equals 0 up to capital N of these numbers in the sequence. So if we wanted to define this for up to infinity, instead of an n, a real a number n, I need stronger coffee this morning. So I can express it like this. I will take the limit of this series as n approaches infinity, right? So there is, as n gets higher and higher, perhaps this expression will approach some limit, perhaps. So this only applies if the limit exists. And if the limit exists, then we can rewrite this as n equals 0 up to infinity of a of n. Okay. Otherwise, if the limit doesn't exist, then well, we'll see examples of limits that don't exist. But then it's pointless because the value of this will depend on the value of n. So writing it like this is meaningless. It'll be infinity. All right. Questions so far? Okay. Am I frozen? Yeah. Sorry, technical difficulties. It always seems that it crashes once, and then it's usually good for the rest of the class. Okay, well, that's, now where were we? Okay. All right, so this is where we were. So if the limit exists, we can write it as this. Otherwise, if the limit does not exist, then it's meaningless to express it this way. Okay, so assuming the limit exists, so we'll consider a series where we define each term an as x to the power n. So this is a geometric series, right, where x is somewhere between 0 and 1. If x was actually 1 or greater, then summing it up, this would have no limit, right? So n to infinity, even if all of an was equal to 1, if I summed up all the numbers from 1 to infinity, then of course I have infinity, and then this becomes nonsense. So when we're summing a geometric series, then the x has to be between 0 and 1, otherwise there is no limit. So if I can express my, if my an is expressed as x to the power n for some value between 0 and 1, then this has a limit. And our claim is that the limit is this expression here. All right, so as n approaches infinity, I have 1 minus x to the power capital N plus 1 over 1 minus x. So that's the claim, and we can prove it using induction, which perhaps we did in 1805, I don't remember. So we can do induction on this capital N and then show that it holds in general. However, there's also another way we can prove it. So if we take this expression here, we want to show that essentially, sorry, 1 second. We want to show that if we ignore this limit part here, that we can express this series as this closed form. So what we're going to do is we're going to write out this series as these numbers. We're just going to write it out explicitly. So for x to the power 0, we get 1 because anything to the power 0 is 1. For x to the power 1, we get x, of course, and then we have x squared next, plus x cubed, all the way up to x to the power capital N, which we have here. And then our claim is that this is equal to this closed form, which we have written here. So how can we show this? Well, what we're going to do is we're going to multiply both sides by this denominator here, this 1 minus x. So here is the same expression again. I'm going to multiply the left-hand side and the right-hand side by 1 minus x. This will, of course, cancel this off. And then I will have 1 minus x times this, this summation. Okay, so now I have this expression, and if I want to write it out, I can simply multiply 1 times this entire thing, and then multiply negative x times this entire thing. So if I multiply 1 times this, I get 1 plus x squared plus x cubed up to x to the power n. If I multiply then everything times negative x, I get negative x times 1 is negative x. Negative x times x is negative x squared. Negative x times x squared is negative x cubed. All the way down to negative x times x to the power n. Sorry, this should be minus, which is, sorry, 1 second. I just have to reset the interpreter here. All right, so then there's a term here, x to the n minus 1. So x times x to the n minus 1 is negative x to the n, and then negative x to the n plus 1, right? So that's this negative x times x to the power n. So multiplying out these two terms, this is the expression that I get. And then you'll notice, of course, that this plus x and minus x will cancel out. This plus x squared and minus x squared will cancel out. This plus x cubed and minus x cubed will cancel out. Everything will cancel out except for the 1 and the negative x to the n plus 1. All right, so, and then, so we have 1 minus x to the n plus 1 is equal to 1 minus x to the n plus 1. All right, sorry, was there a question?
Yeah, I'm sorry, can you go back to how we got x raised to power n plus 1?
Yeah, so here, let's, I'm going to just, because I did do all this neatly. So if I take the left-hand side of this expression, I take 1 times everything, right? So that's going to be this top line. So 1 times everything in here is, of course, just everything in here, right? So this is, not surprisingly, we get this. And then I take this negative x term. So let's get rid of all that. Now I'm going to look strictly at this, and now I'm going to multiply negative x times everything in here. So when I do that, I get, well, negative x times 1 gives me negative x. Negative x times positive x gives me negative x squared. Negative x times x squared gives me negative x cubed. I do have in here a term that I didn't write, but I should be there. So negative x times x to the n minus 1 is negative x to the n. And then finally, the last thing I do is this negative x times this x to the power n. So x to the times x to the power n is equal to x to the power n plus 1. And since this is a negative x, then we have a negative x to the n plus 1. Okay. Does that make sense, or?
Yeah, I got it. Thank
Okay,
you.
no problem. Any other questions? Okay, so then, of course, as we discussed, all of these terms will cancel out. And we are left with 1 minus x to the n plus 1 on the left-hand side of this expression. On the right-hand side of this expression, we still have the same old thing. The right-hand side is 1 minus x to the n plus 1. So we can see that these two expressions are equivalent. And then, of course, we can express the left-hand side as n equals 0 to capital N of x to the n. So these two things, this and this, are equivalent as well. Okay, so since this and this are equivalent, then the limit as n approaches infinity is also equivalent. So that means this is equal to the limit of this closed form expression as n approaches infinity. So what do we know now? We know that n approaches infinity, and we see that n occurs here, and we know that x is between 0 and 1. So what happens if we raise some value x to infinity, or to some value n as n approaches infinity? So then what does this approach? Converges to, it converges to, since, well, let's consider, let's say x is equal to 1/2. So 1/2 to the 1 is 1/2. 1/2 squared is, of course, 1/4. 1/2 cubed is 1/8. 1/2 to the 4 is 1/16. So this value gets smaller and smaller the higher I raise this exponent to. And so it's approaching 0, actually. Yeah. So for an x between 0 and 1, which we could express as a fraction, The limit of x to the n plus 1 as n approaches infinity is 0. So that means if we go back to this expression here, the limit of this as n approaches infinity, this becomes 0, and we're left with 1 over 1 minus x. Okay, so right, so now we have this infinite series right here that we can express in this closed form 1 over 1 minus x. So we're going to use that to help determine our probability of our infinite sample space. All right, questions? Okay. All right, so now we have this that we can use. We can test it out for x equals 1/2. So let's say that we have an infinite series of n equals 0 to infinity of 1/2 to the power n. Well, that is equal to 1. So when n is 0, 1/2 raised to the 0 is 1. When n is 1, 1/2 raised to the 1 is 1/2. When n is 2, 1/2 raised to the 2 is 1/4, and then 1/8, etc. And then if we plug in our 1/2 into this expression, so 1 over 1 minus 1/2, which is what we have here. So that is equal to 1 over 1/2, which is, you can either invert this and multiply, or you can consider, 1 divided by 0.5, or whatever you do, it's going to be equal to 2. All right, so then, yeah, the limit, or sorry, the sum of this expression, this infinite series is, it sums up to 2. All right, good. Questions on that? And we can kind of see this visually, right? So if I have a line from 0 to 2, and then I take each of these and I plunk them down on my line. So I'll take each of these terms, and then so number 1 goes down first. So 1 represents this interval from 0 up to here. This would be 1. Then I want to add a length of the line of 1/2. So this next interval would be 1/2 of 1. And then I want to add 1/4. So I'll put another interval that is 1/4 of the line. And then you'll notice that I have 1/4 left. And I'm going to take 1/8 of that, yeah, so there's 1/4 left here. I don't want to misspeak here. And I'm going to take half of it, which is 1/8 of that, of the full line. Not of the full line. 1/8 of 1 unit of the line. All right, and then 1/16. So each time I'm simply just taking half of whatever's left, and we can see that we approach 2, but we never actually get there. But if we assume that it's infinite, then we will get there. But isn't it supposed to be between 0 and 1? Yeah, so this is the term that has to be between 0 and 1. So what happens is that we start at 0, which means that anything raised to the power 0 gives us 1. So any series of this type, the first term was going to be 1 because it starts x raised to the 0. And so, yeah, we get something. So yeah, what you're saying is the probability of my infinite sample space should be 1. So we're going to see how we can use this to show that. This is just an example unrelated to sample spaces. All right. Questions on that? Okay, so now back to our game of flipping a coin until it comes up heads. Poor Rosenkrantz or Guildenstern, I think it was Guildenstern, still flipping the coin away. And again, any individual member of our sample space, we know the probability of, but we want to sum the probabilities of all the members of our sample space, right? And we want to make sure that all of these sum to 1, the probabilities of each of these. So to sum all the probabilities in the sample space S, we can take the series from 0 to infinity. Now we know the game ends as soon as we flip heads. It is possible that we have 0 tails there. And tails can be any number up to, but I suppose not including infinity. So we can express this function like this. So it's the sum of each of these individual probabilities, and we know that each individual probability can be expressed like this. All right, so it's the sum from n equals 0 up to infinity of 1/2 to the n plus 1. So this is the sum of the probabilities in the sample space. Okay, so now we want to show, of course, that this is equal to 1, hopefully. So what we're going to do is, well, this is actually equal to n equals 0 to infinity, 1/2 to the n times 1/2. So yeah, you can barely see it, but let's pretend that that's 1/2. Since that is a constant that does not depend on this value n, we can take it out in front of the series, front of the summation sign here. So that is equal to 1/2 times whatever this sums up to. However, now we have exactly the series, the infinite series that we saw before, where we summed up 1/2 to the power n from n equals 0 to infinity. All right, so that, if you recall from the last slide, is actually just 2. So we have 1/2 times 2, or we can, or we can explicitly plug this, plug the 1/2 into this expression. So we get 1 over 1 minus 1/2, which equals 1/2 times 2, which equals 1. So if we sum up all the probabilities in our sample space, we get 1. All right. Any questions on that? All right, good. So now we have an infinite sample space. Now we can, and we have, sort of an understanding of it. Now we can use it to play some games. Yeah, we can also think of it as, if I took every element in my sample space and summed all the probabilities, well, then that's the probabilities that I get heads, plus the probabilities that I get tails and then heads, plus the probability that I get tails, tails, heads. And if you summed each of these individual probabilities, well, this is 1/2. The probability of tails and heads, well, the probability that I get tails is 1/2, and the probability that I get heads is 1/2. So since these are independent, multiplying them together, I get 1/4. The probability that I get tails, tails, heads is 1/2 times 1/2 times 1/2 equals 1/8. Oops. And then this one has probability 1/16, etc. And then this is the same number line as before, the same series, except instead of, I used to have 1 plus that, and now I take away that, so that is equal to 1. Yeah, just this is no different from what we looked at before, except for it's just expressed slightly different. So if it confuses you and the other one makes sense, then go with that one. If this helps your understanding, then all the better. Okay, so let's use our newfound tools, our new infinite sample space, and figure out what happens in this game. So let's consider a game. We have one fair coin and players P1 and P2 take turns flipping the coin. And the first player to flip heads wins. So P1 flips tails, P1 always goes first. So yeah, player one always goes first. That's pretty important. Who do we expect to win? I guess might be P2 gets tails, we keep going, P1 gets tails, and P2 gets heads, P2 wins. But yeah, but in general, we would expect player one to win. Player one goes first, maybe they flip heads right off the bat. And in fact, they have probability 0.5 of flipping heads in the first one. So that means there's at least an even chance they win, but probably more than that, right? So we are going to verify this intuition. So yeah, this does not seem like a very fair game because player one, if for a 50-50 shot that they lost the first round and a 50-50 shot that they win, and then after that, they still have a chance to win in addition to the 0.5 that we see here. So yeah, not a very fair game. But the sample space is exactly the sample space we were looking at before. So there's a series of coin flips, and the coin flips end as soon as we flip heads. So we can, we know the probabilities of each of these events. We just have to figure out, now we have to split these events into two separate events where player one wins and the events where player two wins. All right, so event A is the event that player one wins. So A, of course, is a subset of our sample space. So what outcomes does A contain? Well, if we look at it, player one wins here if they flip heads on the first coin flip, or they win here if they flip heads on the third coin flip, or if we had more coin flips, they would win here. This is the fifth coin flip, right? So this is the first, second, third, fourth, fifth. So every odd coin flip, if it comes up heads, player one wins. And every even coin flip, if it comes up heads, player two wins. So that's how we can, yeah. So if we take our sample space here, then if I flip heads on the third coin flip, that means I have flipped an even number of tails before that. So, and if I flipped heads, yeah, if I flipped heads here on the fifth coin flip, then again, I have an even number of tails before that. I have 4 flips of tails. So the event A contains all of the elements of S where n is an even number. So A is the event player one wins, and A consists of these. So just heads, or 2 tails and then heads, or 4 tails and then heads, or 6 tails and then heads, etc. So all of these events. So this is also an infinite set, right? Because there's no, this can go up to infinity. So A, the event A is, if we want to express, we take some integer m that's at least 0 and multiply by 2, then we can ensure that 2m is an even number, right? So this 2m represents some even number of flips of tails times heads, and this is our sample space for A. So now we want to, so we knew how to compute, I guess, the sum of the probabilities for this, since this is all of the elements in our sample space, where n is at least 0. So now we want to apply sort of the same strategy to this. So the probability of event A is the sum of all of the individual probabilities of each outcome in a and there are infinitely many of them. But we have some tools now that we can use, most notably this expression. Okay, so the probability of A is equal to the sum of all the probabilities from m equals 0 to infinity, where we have some even number of coin flips that come up tails and followed by one coin flip coming up heads. We know each coin flip is independent, so we can express the product of each outcome as the product of the probabilities of the coin flips. So we can replace this term with the probability that we flip tails raised to the power 2m times the probability of heads. So what's happening is I have, the probability here, really, this should read something like this. Dot, 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 up to h. And since these are all independent, we can express it as the product of all of the probabilities. So then this is equal to probability of tails times probability of tails times probability of tails, some even number of times, and then times the probability of heads. So the number of these times that we flipped tails is 2m, because it's some even number, and then this is, of course, we flip once. So this is where this 2m comes from, times the probability of heads. It would just be half the old answer we got before. It almost seems that way, doesn't it? But not quite, because we also have this. Well, let's keep going and see what. Let's take this. Okay, so I know the probability, each of these individual probabilities is 1/2, right? So probability of tails equals 1/2. Probability of heads equals 1/2. So I have this becomes 1/2 raised to the 2m times 1/2. So it is similar to what we had before, but now we have this extra 2 in the exponent. So how do we account for that? Well, the same as we did before, we can take this 1/2, since it is a constant, it is not dependent on any variable, and we can bring it out front. And then we can take this 2m, which is simply, 1/2 times 1/2 times 1/2, and then m times, let's see, what's a better way to do this, up to, so there's 2m of these. So if we take every pair and pair them together, we have m pairs, right? So then each pair becomes 1/2 times 1/2, and then there are m of these pairs. So it's 1/2 times 1/2 raised to the power m. 1/2 times 1/2 is, of course, 1/4, raised to the power m, and then we have 1/2 out here. So we have now this, which we can express using our formula here. So this is equal to 1/1 minus x, which is, the x is 1/4, so 1/1 minus 1/4, and then we can multiply by 1/2. This is equal to 1/2 times 1 over, so 1 minus 1/4 is 3/4. If you invert and multiply, you get 1/2 times 4/3, and then the 2 will cancel with one of these 2's, and we get 2/3, which if we wanted to look at that in a lot neater fashion, it would look like this. Okay, so not quite 1/2. It's 2/3 chance. The probability that player 1 wins is 2/3. All right. Questions on any of this? Are we going to use some other infinite series to solve certain probability problems, or is this the main one that we're going to use? What do you mean by other infinite series? So we'll use mainly, if it's infinite, then we're going to be using this. Of course, the trick is to sort of mix up the probabilities a bit on you, or, you know, or throw in some curveballs like this. This is stuff that's on assignment 4. This is actually the first question on assignment 4. Is this infinite series stuff? It's not that hard. If you understand this, you're probably going to do fine. Of course, it's always more difficult to apply it. When you see it and you go, oh yeah, that's no problem. Then you see a question, you go, what was I supposed to do again? Right. Any questions though on Okay, so we have, yeah, another way we could have written this is, since all of these have the same probability, whether it's tails or heads, we could write this as 1/2 to the 2m plus 1, which is, of course, everything works out exactly the same. I just take this plus 1, which is simply a half. I bring that out front. The 2m, 1/2 to the 2m becomes 1/4 to the m, and we get the exact same answer. So yeah, there's nothing different going on here. Just this first step, we skipped some of the intermediate stuff and went right to right from here to here. That's how you feel with every assignment question. Yeah, no, and that's, man, me too. All right. So the probability that player 1 wins is 2/3. Of course, since there's only these 2 possible outcomes in our game, we know that the probability that player 2 wins is equal to 1/3, because 2/3 plus 1/3 must sum to 1. So we can, yeah, so the probability that player 2 wins, we could express as 1 minus the probability that player 1 wins. So that's 1/3. Or we can, if we use the same technique to express this explicitly, well, player 2 wins if there's an odd number of tails. This should be -1. How did I get that so wrong? 2m. Oh no, m is 0, so that's +1. Yeah, that's right. Okay, no problem. Whew. Okay, so if tails wins, we can, if player 2 wins, we can express it like this, where we have an odd number of tails, and then each of these, of course, has probability 1/2. So instead of 2m plus 1 to the 1/2 times 1/2 gives me 2m plus 2 to the 1/2. And then from here, of course, I can do the same thing I did before. I take out this constant. So this is times 1/2 to the power 2. And then this is 1/2 to the 2m. And then everything's the same after that. 1/2 squared is, of course, 1/4. And I take that out front because it's a constant. This part becomes 1/2 times 1/2 to the m, which is 1/4 to the m. So I get, yeah, I still get the same 4/3 here, but instead of times 1/2, it's times 1/4, and I get 1/3 for the player 2 winning. So yeah, we didn't have to do that. We could just use the, you know, the idea that there's only these 2 possible outcomes, and they must sum to 1. But you know, a little bit of extra practice doesn't hurt. All right, questions? Okay. Let's take this a little bit further then. We're going to take a new game. We have a fair coin. Basically, it's a variation of this old game. So we have player 1 and player 2 take turns flipping the coin, and the second player to flip heads wins. Okay, so there's a couple ways we could approach this. We'll do them both. One is an exercise from the textbook, but it's pretty neat. So we should, we'll do it the hard way, or not the hard way, but the, I guess, complete way first, and then we'll show you a trick that makes it much simpler. So if A is the event that player 1 wins, we want to determine the probability of A. And also, who do we think now has the higher chance of winning, player 1 or player 2? If the second person to flip heads wins. Yeah, it seems like it might go to player 2 now. Because if player 1 has a better chance of winning for the first heads, so let's see here, do I have an example? Yeah, so if we play the game and I know that player 1 has a better chance of flipping heads the first time, then that means player 2 is going to start, in some sense, the next round. So if player 2 flips first, then player 2 has a better chance of winning than player 1. So yeah, it seems like it's going to flip in player 2's favor, but let's take a look. So some of the outcomes might look like this. We get the first heads in the fourth flip, and then we get 2 more tails followed by heads. And this is just to kind of, it's just a meaningless delimiter here, just to sort of separate where we get our first heads from where we get our second heads. So yeah, here are what some of the outcomes might look like. So our sample space looks something like this. I have n number of tails followed by heads, followed by m number of tails, followed by a second heads. And where n and m are some integer that it's at least 0. So again, for player 1 to win, the second head must be on an even flip. Is that right? That should be odd flip, eh? Did I get that wrong? Player 1, yeah. Odd flip. All right, so our sample space is this. Yeah, okay, I got it right here. For some reason, I wrote it wrong on the other slide. All right, so the second heads must be on an odd flip. So that means n plus m plus 1 must be an even number, since that is the number of flips before I flip my second heads. Right, so I have n tails plus 1 plus m tails here. So there are 2 ways for this number here to be even. Either n is odd and m is even, or m is odd and n is even, right? So if n is odd, maybe it's 3, and m is even, maybe it's 4. And then I add 1 to that, I get 8, which is an even number. And then my second flip of heads is on an odd number. Yeah, hey, I got confused too, so no judgment. All right. So if n is odd, then m must be even, and if m is odd, then n must be even. So we have 2 separate cases that we're going to look at. So we want to express the event A that player 1 wins in terms of these subsets, which is something that we've done before. We'll have A1 be the event that player 1 wins and n is odd, and A2 be the event that player 1 wins and m is odd. Okay, so observe that A1 and A2 are disjoint, right? Because if I have some sequence of coin flips where n is odd, and then another sequence where n is even, they cannot possibly have any elements in common, right? That is, yeah. So A1 and A2 do not share any elements because n is either odd or even, which means that right away they're going to look different. So since they're disjoint, we can use the sum rule. So the probability of A is the probability of A1 plus the probability of A2. And as before, the coin flips are independent. So if we want to determine A1, where m is even, we can write m is equal to 2k, since that would be an even number. And n is odd, so we want n is equal to 2j plus 1, right? So that's how we would express an odd number. So now we can express our probability of A1 by this expression, right? So we have some odd number of tails here, followed by heads, followed by some even number of tails, followed by heads. This is simply A1. This is not the total probability of A yet. Independent events theorem is basically the product rule, yes, as long as it's the intersection of these events. If a bunch of events are independent and they all happen, then the probability of all of them happening is the product of their probabilities. Yeah. Like I said, if we have time, I'll get into some short little exercises that sort of use these in a very easy environment, so you can kind of get used to them. Because yeah, we often use the idea of sets being disjoint and also the idea of sets being independent, and it's important to keep those two concepts clear. All right. Okay, so j goes from 0 to infinity, k goes from 0 to infinity, so all possible combinations of these numbers will give us every possible event in this, every possible outcome in this event space. So if we express that, we get, since each of these coin flips is independent, we can, and each of them has probability 1/2, we get 2j plus 1, 1/2 raised to the 2j plus 1 plus 2k plus 2 for these 2h for the two heads. Maybe I should I'll make this a little more explicit here. 1/2 2j plus 1 plus 2k plus 2 for the two heads. And then I add this 1 and 2 together and I get plus 3. So since all of these coins are flipped independently, the probability of A1 can be expressed like this. So now again, we have something similar to before, but we have to use a few more rules of summation to get to the final answer. All right, so from here, we know that we can split this into, if we just look at this term, this is 1/2 to the 2j plus 3 times 1/2 to the 2k. The thing is the 2j plus 3 in this summation is a constant, right? Because in this summation, k is the variable. So this part of the term changes with the value k, but this part does not. So we can move this, it acts as a constant, we can move it outside of that series. It's getting a little complicated here. Any questions on this? This is these are sort of stuff we learned in 1805, but I get, that was a long time ago. So how the exponents were derived? Sure. Yeah, I did skip a couple steps in this one. So the event A1, let's see here, maybe I can, is where we have m equals 2k. So A1 is the event, it's the set of all elements t, was it, n is odd here, right? So 2j plus 1. So odd number of tails and a head, and then even number of tails and then heads for m greater than or equal to 0 and n greater, or sorry, j greater than or equal to 0 and should be k greater than or equal to 0. Okay, so we're taking this event A1, which is player 1 wins and n is odd. N is the first set of tails, so we can express it like this. So A1 is the set of all of these events. So now we know that, yeah, the probability of A1 is the sum of the probabilities of each of these. So, yeah, how would we express that? Well, we would simply express it like this. So it is the sum. Yeah, well, I wrote it out already, but all right, all right, I'll do it. It's a bit of a pain, but j equals 0 to infinity and k equals 0 to infinity of the probability of each of the individual probabilities of every element in this event space. So this is, yeah, 2j plus 1 times h times t to the 2k times h. Okay, now for each of these individual terms, we know that the coin flips are independent. So we can express this for any particular value, 2j plus 1h t to the 2k times h is equal to the probability of t times probability of t times the probability of t, 2j plus 1 times. So that's the probability of t to the 2j plus 1 times the probability of h times the probability of t times the probability of t times the probability of t 2k times times the probability of h again. That's because the coin flips are all independent. Each of these probabilities is equal to 1/2. So I'm running out of space, so I'm going to move over here. So it's 1/2 to the 2j plus 1 times 1/2 times 1/2 to the 2k for this term times 1/2 for the heads. So this probability of A1, so each of these individual terms in this summation is equal to this. And then we can, since these are all 1/2, well, we have 2j plus 1 of 1/2 here and 1 here, 2k, so yeah, let's write that out. 2j plus 1 plus 1 plus 2k plus 1. Right? So we just take each of these individual, you can think of these as having an exponent of 1. So we add all of those exponents, and then we get 1/2 times 2j plus 2k plus 3. So yeah, this is how we get, and then so we can take this number and plug it in for this probability here, and we get 1/2 to the 2j plus 2k plus 3. All right, so then this is what, well, this here is what we want to work out using our 1805 summation laws. So yeah, that's basically all of these steps that I just showed you are steps that I skipped here in this, but yeah, so all the stuff I wrote would go in here. Okay, so now we have to evaluate, see what this evaluates to. Again, since this is the summation where k is the variable, that means this 2j acts as a constant. and this +3 acts as a constant. So we can take this 1/2 to the 2j plus 3, since these are constants in this series, and take them outside of the series. Of course, j is not a constant here, but now we have an infinite series that we actually know how to solve. And we have actually a second infinite series that we know how to solve, and we're just going to multiply them together. So this one, the +3, so we could write this as j equals 0 to infinity of 1/2 to the 2j times 1/2 to the 3. So this is a constant, so we can bring that out in front. And then we still have this. So this is equal to 1/2 raised to the 3 times this infinite series to the 2j times this infinite series to the 2k. Luckily, we know how to solve these. This is simply, each one of these is, if I took, for instance, the k is 1/2 times 1/2 to the k, right? So I take this 2, so I take every pair of these 1/2s and I put them together, raised to the power k, so I get 1/4 to the power k. And here I get 1/4 to the power j, and all of that times 1/8. Each of these individually I know how to solve. No, yeah, I didn't really do the, so yeah, now I'm going to use my expression here again to solve these infinite geometric series. So this side is 1/1 minus 3/4, sorry, over 1/4. Yes. And of course, this side is 1/1 minus 1/4. So the x, this 1/4 gets substituted in for the x, so it should be 1/4. I'll get that straightened out on the slides and post it later. And then it's simply, this becomes 4/3. This one becomes 4/3, and we have our 1/8. So it is 16/72, which is 2/9. That's for A1. All right. So once again, this is all stuff that we've seen already, except we're just doing it in a way more complicated form, where we have to, think back to 1805 and how we handle summations, where there are two summations or nested summations. But yeah, once we get it down into this form, it's pretty straightforward. It's simply substituting this in. We have our constant out front. So this is going to evaluate to some value. This will evaluate to some value, and we will multiply all three of these values together to get our final probability of A1. Questions? How are we doing for time? This is taking longer than I thought. All right, so we won't get, it's all right. A2 is the exact same thing, except we have m is equal to 2k plus 1, since it's going to be odd, and n is going to be 2j since it is even. So, however, we end up really with the same expression. We have 1/2 raised to the 2j plus 2k plus 3. So this is precisely the same probability as A1 was. So we get 2/9 here as well. All right, so finally, we know that these two events are disjoint. So we can use the sum rule to determine the probability of A. So we get 2/9 plus 2/9 is 4/9. So the probability that player 1 wins is now 4/9. And because player 2 wins is equal to basically A bar, we can use the fact that player 1 winning and player 2 winning is equal to the entire sample space. So player 2 winning, the probability is now 5/9, since those must add up to 1. So the odds have shifted into player 2 favor, as we suspected. Okay. Questions? All right, do we have time to 42? We have 10 minutes left, roughly. All right, we can think of this, we can look at this. Let's try and show this in the easier way. So we're going to take our first game where the first player to flip heads wins. And we're going to define it by these events, BIJ. So BIJ means player I starts the game and player J wins the game. I and J are some value, either 1 or 2. So we know that the player that starts the game is expected probably going to win the game, right? So the player that starts the game is more likely to flip the first heads. So the probability of B11 or B22 is 2/3. And the probability that if player 1 wins and player 2, or sorry, if player 1 starts and player 2 wins, that has a probability of 1/3. And likewise, if player 2 starts but player 1 wins, that also has a probability of 1/3. So this is back to our original game. So we're going to frame this game now as 2 rounds of our original game. So yeah, the second player to flip heads wins. So A is the event that player 1 wins. Again, we have this same sample space. So these are all the possible events, but we can think of it as 2 rounds of the first game. So we can have either, this can be either event, B11, where player 1 starts and player 1 wins, or it can be B12, where player 1 starts and player 2 wins. So player 1 always starts. So this first round can be thought of either this event or this event. Then the second round depends on who wins the first round. So if player 1 flipped that head, then player 2 would start the second round. So if player 2 then wins, then player 2 starts, player 2 wins, that's event B22. And if player 2 starts and player 1 wins, that's event B21. So yeah, so we're going to, instead of going to all that trouble that we went to before, we're going to take the simple version of this game, define a bunch of events based on that, and then use that to solve this problem. Questions on the premise? All right. So round 1 ends once the first heads is flipped, and round 2 ends once the second heads is flipped, and whoever wins round 1, the other player, the opposite player, will start round 2. So now we can look at, yeah. So A is the event player 1 wins the first round, and player 1 wins the second round, or player 2 wins the first round and player 1 wins the second round. So we can, right. So let's look at, we're going to express this as the union of 2 separate events. So this will be event A1, and this will be event A2, and they are, this OR represents the union of these 2 sets. So we could define A1 as player 1 wins the first round and player 1 wins the second round. And A2 is player 2 wins the first round and player 1 wins the second round. So A1 or A occurs if A1 or A2 occurs. And these are, again, disjoint events. So we can have probability of A equals the probability of A1 plus the probability of A2. So the probability of A1, again, we talked about how this is, this and in English is also a logical and. It's also the intersection of these 2 events. So we can rewrite A1 and A2 in terms of these events over here. So A1 is player 1 wins the first round and player 1 wins the second round. So we know that player one starts the first round and player one wins the first round. So that's event B11. If player one wins the first round, then player two must start the second round. So then we're assuming that player one won the second round. So this is event B21, right? So then A1 is the intersection of these two events. Yeah, so we write intersection here as an and, but when we go to compute the probability, we will use the set intersection. Similarly, we can define A2 in terms of these events. So P2 wins first and P1 wins the second round. So P1 starts the first round and P2 wins the first round. So that is event B12. If P2 wins the first round, then P1 starts the second round and P1 wins the second round. So that's event B11. Thus, A2 is B12 and B11. Those two events must happen for A2 to happen. Okay, so now we can define our events A1 and A2 in this fashion. B11 and B21, are they independent events? So I guess the proper way to do this is with conditional probability, but if we just consider they are independent events, right? Because I'm saying player two starts this round and player one wins. And I'm saying player one starts this round and player one wins. I know that I chose this event because player one won here, but the probability of this event is independent of the probability of this event, right? So if this event happens, yeah, that does not change the probability of this event, if that makes sense. So in some sense, in our game, they are dependent because I'm saying, well, this can only happen if this happens, but the probability of this is independent because these are all independent coin flips. So B21 is the event that P1 wins, given that P2 started. And if P2 started, P1 won last round. But the two different rounds have no coin tosses in common, so they are independent events. Or consider that the probability of this event B21 happening, given that B11 happened, is still the same. Ideally, you should use conditional probability, but I didn't here. I thought maybe an intuitive understanding of it might be better. But so B11 and B21 are independent, so we can express the probability of A1 as the probability of this event and this event occurring. Since they are independent, it's equal to the probability of B11 times the probability of B21. Probability of B11 is 2/3, B21 is 1/3, so that is equal to 2/9. A2 is events B12 and B11. Again, they are independent, so I can express the probability of A2 as the probability of both of these events happening. Since they are independent, it's the probability of B12 times the probability of B11. So B12 is 1/3. B11 is 2/3. So 1/3 times 2/3 is 2/9. So finally, we have the event A that player one wins. Well, player one wins if A1 happens or if A2 happens. Since these are disjoint sets, we can use the sum rule. So it's 2/9 plus 2/9, which is 4/9, which was the same answer that we got before. But just, using what we knew in a clever way. All right, questions on that? All right. So what happens if we go to 3 now? Now, who do we think is going to win? we won't go through it. But so every time you flip, it's, in this case, we would think that player one now would have the better chance of winning, but it's going to get closer and closer to 0.5, right? So we could take it, the third flip, the fourth flip, the fifth flip, and every odd flip, the probability will shift in favor of player one, and every even flip, the probability will shift into favor of player two. And we could actually figure this out using these events. So now it becomes 3 rounds. We could do the exact same thing as before. However, we might notice that we're wondering what to put in these question marks. Well, if 2 wins here, then 1 must start. And if 1 wins here, then 2 must start. So if we actually, all 4 of these question marks are determined by whatever we have in the middle here. So we can write this, once we put every single possible event in the middle, we have all possible ways that player one can win, right? Because these numbers will determine these numbers here. And then, yeah, we're not going to go through this, but if you are interested, you can take a look on these slides and see. Works out the exact same. These are all independent events, so I multiply the probabilities. I determine the probabilities of A1, A2, A3, and A4, which is, so at this point, I'm doing these slides, and I got 2 over 27 here, I got 2 over 27 here, I got 2 over 27 here, and then I'm like, this is probably 2 over 27. I didn't even check, and then I'm like, why am I only getting 8 over 27? This doesn't make any sense. And then, yeah, I guess I was tired. It took me a while to realize, oh wait, this is not all symmetric. These are all equal to 2/3, but yeah. So then the probability of player one winning is the sum of all of these probabilities, which is 14 over 27. So it just shifts in favor of player one again, but only by a little bit over 0.5. All right, I guess that took longer than I thought, so we will stop there today. I can answer any questions you have, but otherwise, what's today, Thursday? Yeah. So have a good weekend, good luck on the assignment, and I will see you guys next week.